Hi viewers, I am Devdas. In this video, I like to explain about Beer-Lamberts law. Beer-Lamberts law is useful in quantification of most of the organic, inorganic and biological molecules. Let's have a look on principles of spectrophotometry. Bauger is considered as father of photometry. Photometry stands for measurement of photons intensity, that is photons population. Bauger's law expresses the relationship between the absorption of radiant energy and the absorbing medium. J.H. Lambert, he has proposed an equation called Lambert's law, Lambert's equation. Observe carefully this picture, dear students. This solution is filled with some chemical species. This I naught represents the intensity of the light before passed through this sample placed in a container, cuvette, and I, sometimes called IT, is the intensity of the light after passing through the sample. Therefore, when electromagnetic radiation is allowed to pass through a liquid medium which is filled with a chemical dissolved and it is devoid of particulate matter, clear, transparent. So what happens? A part of the incident light is reflected, a part is absorbed by the medium if the chemical species is able to absorb the radiant energy. Some part of the radiant energy or radiation may be transmitted as such, that is called unabsorbed. It is nothing but the transmitted light. Therefore, the intensity of the monochromatic light is a sum of radiant energy reflected, IR, IA, intensity of the radiation absorbed, and IT, so the value of IR, the intensity of the reflected, can be neglected for a transparent medium or a glass interface. Therefore, I naught equals to IA plus IT, where IA, the intensity of the radiation absorbed, IT, the intensity of the radiation transmitted. If any absorption of electromagnetic radiation by the medium, the intensity of the emergent light is less than that of the incident light, which can be seen in the picture. I naught is thicker, IT is observed thin due to some absorption when the container filled with a sample. Beer's law, the intensity of a monochromatic radiation decreases exponentially with the increase in the concentration of absorbing species arithmetically. That means, if the chemical species concentration is increased, so the emergent light beam crossing through the chemical species is usually decreased. This relationship can be mathematically expressed as minus di to dc proportional to I. And then in order to remove a proportion, we introduce a constant k. So, the second equation becomes minus di by dc equals to ki. By rearranging the terms, minus di by I equals to k dc upon integration. So, this minus sign indicating the transmitted light intensity is going to decline. So, minus integral of di by I equals to k integral dc minus natural logarithm I or negative natural logarithm I equals to kc plus b. So, upon solving the integral equation, we got what is negative natural logarithm I equals to kc plus b, where b is a proportionality constant. When the c term is 0, there would be no absorption, hence I becomes I naught. Here I stands for IT or transmitted radiation. I naught stands for the intensity of incident light. So, substituting the value of I in equation 1. So, this is equation 1, negative natural logarithm I equals to kc plus b. So, what we are doing here, so this I becomes I naught and the c term is 0. So, submission of these values on equation 1, negative natural logarithm I naught instead of I, we written here I naught equals to k into c term here 0 plus b. So, the value of b can be derived from this equation as negative natural logarithm I naught. Now, let us substitute the b value in equation 1. So, that is equation 1, negative natural logarithm I equals to kc plus b. So, upon submission of b value on equation 1, negative natural logarithm I equals to kc minus negative natural logarithm I naught. Instead of kc plus b, b value is a negative value, therefore kc minus natural logarithm I naught. So, let us rearrange the terms to get the value of kc. So, when kc is solved, to get natural logarithm I naught by I equals to kc, removing the natural logarithm, I naught by I equals to e power kc. When making inverse on both sides of the equation, So just inversing I naught by I, we get I by I naught equals to e power minus kc, and it can be rewritten as I equals to I naught into e power minus kc. This equation is called equation for Beer's law. Similarly, Lambert's law, the rate of decrease of intensity of monochromatic light with the thickness or path length of the absorbing medium is directly proportional to the intensity of the incident light. So what happened here, the intensity of monochromatic light decreases here also with the parameter called increase in the thickness of the absorbing medium or path length of the absorbing medium. So this relation can be mathematically expressed as minus di by dt proportional to I. Remember, capital I stands for the intensity of the transmitted light, which is going to be declined. That is why the negative sign incorporated here. Wherever you see I naught, it means the intensity of the incident light before passed through the solution. So like Beer's law, Lambert's law equation can also be summarized, solved to get the equation for Lambert's law as I equals to I naught into e power minus kt. There, in the case of Beer's law, I equals to I naught into e power minus kc. Instead of c, here we placed t. That t, thickness or path length. Now, let us combine both the equations. That is, I equals to I naught e power minus kc. So, e power minus kc and e power minus kt. So, therefore, both the equations can be combined to get the common equation. This common equation is known as equation for Beer-Lambert's law. That is, I equals to I naught into e power minus kct. So, what happened? We combined both the equations, Beer's law as well as Lambert's law, to get a common expression for Beer-Lambert's law. Now, rearranging the terms, I equals to I naught into 10 power kct. So, I by I naught equals to 10 power minus kct can also be written as like that. Taking inverse on both sides to get rid of negative minus sign, I naught by I equals to 10 power kct. Taking log on both sides, log I naught by I equals to kct, because 10 power kct becomes kct upon application of log value. This log I naught by I can be expressed as A, capital A, nothing but absorbance, K as a constant, C concentration of the solution, T path length, thickness of the absorbing medium. Therefore, A or absorbance can be defined as logarithm to the base 10 of the reciprocal transmittance. So, the reciprocal transmittance 1 by T, its log is called absorbance, its logarithmic value. And in order to remove the reciprocal of transmittance, the A can be written as 2 minus log percentage T. So, absorbance equals to 2 minus log percentage T. So, the instrument measures usually the transmittance. So, they directly measures the transmittance or the transmitted light intensity from which absorbance is derived. Now, absorbance can also be expressed in terms of specific absorbance. It is nothing but the absorbance of 1% weight by volume solution of a drug measured in 1 centimeter cuvette, 1 centimeter cell, which has a fixed path length. So, absorbance of 1 gram per 100 ml solution of a drug molecule gives you the specific absorbance, whose units are deciliter, gram inverse, centimeter inverse. Therefore, Beer-Lambert's law can take another form as A equals to A 1% 1 centimeter into C into T. Here concentration term becomes percent weight by volume or gram per 100 ml. Now, when concentration term expressed in gram per 100 ml or percent weight by volume, the constant K becomes A 1% 1 centimeter specific absorbance. Molar absorptivity epsilon, nothing but the absorbance of 1 mole per liter solution taken in 1 centimeter path length in a cuvette. Now, Beer-Lambert's law can be written as A equals to epsilon C T, where epsilon molar extinction coefficient or molar absorptivity, concentration, path length. The concentration term here moles per liter. Epsilon value less than 100 are weakly absorbing species, whereas epsilon value more than 10,000 are weakly absorbing species. Epsilon values less than 100 are weakly absorbing species, whereas epsilon values more than 10,000 are, so here is a typographical, sorry for the typographical, epsilon value more than 10,000 value of a chemical species is said to be a strongly absorbing species. So, less than 100 weakly absorbing species, greater than 100 epsilon value, greater than 10,000 epsilon value, it is strongly absorbing species. So, the units of molar extinction coefficient, liter mole inverse, centimeter inverse. The units are very important to recognize how the K is expressed, constant is expressed in terms of A 1% 1 centimeter or epsilon molar absorptivity. So, many absorbing drugs, so most of the drug molecules have the epsilon value between 10 power 3.5 to 10 power 4.5 liter mole inverse, centimeter inverse. Relationship between specific absorbance and molar absorbance, molar absorptivity. Epsilon and A 1% 1 centimeter can be interchanged, interconverted by the expression epsilon equals to A 1% 1 centimeter into molecular weight of the species by 10. Absorbance is the reciprocal of the transmittance, whereas let us define the transmittance is the ratio of the radiant power transmitted by the sample IT to the radiant power incident on the sample. So, transmittance can be defined in this way and expressed as T equals to IT by I naught, where IT stands for the radiant power transmitted by the sample, I naught stands for the radiant power incident on the sample. So, this is the discrimination I naught before passed through the solution, IT after passing through the solution. If the transmittance is 50%, that means 50% of the drug may be 50% of the radiant energy is absorbed. Therefore, if percentage transmittance is 50%, the absorbance value is about 0.3. What about the maximum absorbance value? If one wants to get the maximum absorbance value, so the transmittance should be as low as possible, that is 10% for example, so that we get 1%, 10% for 10% transmittance we get absorbance as 1.00. If the transmittance is 0, it means the full quanta of photons absorbed, so the absorbance becomes 2.0, the transmittance would be 0. Therefore, the absorbance value, the maximum absorbance value is 0 to 2, that is 2.00, whereas the transmittance range from 0 to 100%. So, this is the absorption spectrum or absorption curve of potassium permanganate. So, different concentrations of the solutions are prepared and scanned in a recording spectrophotometer. So, all the solutions gave the same kind of the pattern. This could be useful in identifying a drug molecule. The lambda max is about 500 or 5 to 600 between. Here we see, so this is the lambda max point. So, whatever may be the concentration of the species studied for lambda max, irrespective of the concentration, the lambda max lambda max remains same. What happened? This absorbance, the absorbance is increased. So, for green color solution, absorbance is about 0.2. For purple color solution, absorbance is about 0.7. So, likewise, the lambda max is constant irrespective of the concentration under same experimental conditions. Absorbance is going to be changed depending on the concentration. This indicates the increase in the color intensity of a chemical species. Therefore, the absorbance should increase. So, from the first to last solution, you will be able to notice the color change and the intensity of the color is gradually increased here. What about the absorbance? The absorbance of the solutions also may be increased gradually when plotted on a calibration plot. This plot is known as Beer's plot or external standard curve or the calibration curve. Sometimes it is may be called as a standard curve. So, the standard curve is a plot of concentration on x axis and absorbance on y axis. With the concentration, the previous slide, the color intensity for each color solution, lambda max is same. At that particular lambda max, absorbance is recorded. So, the absorbance corresponding to each and every concentration of the solution is plotted on a Beer's plot. So it nearly gives a straight line with y equals to 136.67x regression line with the correlation coefficient, the square of the correlation coefficient 0.9986, approximately 0.999. So this is an excellent correlation when the concentration and absorbance are linear. So in this way, Beer-Lambert's law can be applied to plot a standard curve or calibration curve from which an unknown concentration of the same drug can be interpolated or can be solved from the regression line y equals to 136.67x in this example. So in this way, the Beer-Lambert's law can be useful for quantification of many of the drug molecules. So hope you understand. Thank you for watching and listening. Thank you very much.